Hi, this is Jessica Kittner, and in this video I'm going to show you how to use Gauss's law to find the electric field due to an infinite sheet of charge. You could, if you saw this problem in a textbook, it might look something like this. An infinite sheet has a surface charge density of sigma. The sheet is in the horizontal plane. Assume it is infinitely long and wide and infinitesimally thin. Find the electric field at distance h above the sheet. It might sound like kind of a silly problem to tackle an infinite sheet, but it makes the symmetry very nice and makes it easy to solve. And it turns out that it's a good approximation for any plane of charge whenever you're close enough to the plane. It's a good approximation, so it's useful to do it this way. Here's a picture of what I have in mind. So I've drawn the arrows to indicate that the sheet, so the red is the sheet, a perspective view, and there's a charge. May as well assume it's positive for the scope of this problem. Spreading out in the, let's see, the way that I have that drawn, it would be the XZ plane for the sort of standard XYZ axis that I would usually draw, and a height h above the sheet. So let's try to solve this problem. Because it has such a nice symmetry, it's really easily solved using Gauss's law. The only trick when we use Gauss's law is we want to evaluate that left-hand side of the equation. Gauss's law is the closed integral of E dot dA equals Q enclosed over E0, shown in red there. So the trick is to evaluate the integral on the left-hand side, and to make that dot product easy to solve, you want to find a surface, a Gaussian surface that you can draw that is either parallel to the electric field or perpendicular to the electric field, or to make it closed, of course it could have some surfaces parallel and some surfaces perpendicular. So that's a nice trick, and like I said, because this has a plane has good symmetry, that makes it pretty easy to do. So that means we need to know the direction of the electric field before we can figure out what surface would be parallel or perpendicular. So let's see if we can figure that out. I'm going to look at a side view of the sheet and try to make an argument for you about which direction it should be. So there's our, I usually draw an empty box, that box in blue that you can see there up on the top up here. I usually draw an empty box like that just to indicate there's no other point charge or anything in the problem. So a distance h above the sheet, and again that's a side view of the sheet going off in both directions. The z comes straight out of the plane of the screen. I'm going to imagine chopping that sheet up into infinitesimally small pieces, dq, and I'm going to treat each one of those little tiny pieces of charge as if it's a point particle. So I'll draw the direction, I'll draw the vector from the dq to the point I'm interested in, which is the h. So I've drawn this vector here, which I don't need for Gauss's law, but just to show you the picture as if you were treating it like a point charge, and then that little piece of charge dq here causes this little piece of electric field up here. So I can do that, and I can think about each one of those pieces of dq. I can find another piece exactly symmetrically on the other side that will completely cancel out the horizontal component of the electric field. Right, because it's infinite, you can always find a piece on the other side. You can always find another dq that will cancel that out. Let me see if I can show that. So there's our first dq. And there, I've found a second one, and as long as those two distances are the same, as long as x2 is the same as x1, then because the h is the same, they'll be the same triangle, and the DEs will be exactly the same. So the one that I just drew, the second one, which is this one, will be exactly the same as that one. And if those two vectors are exactly the same, then the x components will cancel out because one of them will be in the plus x direction and one of them will be in the minus x direction, and those will completely cancel each other out. Just write that so you can copy it down if you want to. If x2 equals x1, the x components of dE1 and dE2 will cancel. E must be vertically away from the sheet is what that means. So for every DQ we can find everywhere along the sheet, if I start off with all of them on the left-hand side, I can always find another one on the right-hand side to cancel it out. That's actually the same. I could rotate the sheet too, and that's the same with the front and the back. So we know the electric field has to look like this. It has to be vertically away from the sheet. On the top, it's going to be straight up, and on the bottom, it's going to be straight down. The name for the surface we're going to use for our Gaussian surface is called a pillbox. And it's traditionally drawn as a cylinder, a sort of squished cylinder, like I'm trying to show here. So I've got the three faces labeled. So the cylinder basically goes through the sheet. So there's a top face, which is above the sheet, and then it cuts through the sheet, so I've drawn the middle one, and then there's a bottom face that's actually below the sheet. Each one of those sides, oh there, I'm drawing the electric field vectors for you. And then each one of those sides of the Gaussian surface that we drew has an area vector that you need for when you do the E dot dA. So there I've drawn the top one. If you remember, the area vectors are always normal to the surface. So for the top face, normal to the surface is straight, and they always go out. So for the top face, normal is straight up. For the bottom face, normal is straight down. For the side face, I've tried to draw in perspective views where they go off to the side and they point out of the page to radially outward along that cylindrical surface that I've drawn. So once we understand that, we're ready to apply Gauss's law, and we'll have to chop it up into a few pieces, the top, the bottom, and the sides. So the integral of E dot dA is the integral of E of the top times A of the top plus E of the bottom times A of the bottom. Oh, there's one more piece, plus E of the side. That one is going to go away because of the cosine of 90. So the electric field is either straight up or straight down, and all of the side pieces have area vectors that would be in the horizontal plane. It's a perspective drawing, so that might be hard to tell. But if you think about a cylinder that's in the vertical direction, then all of the side pieces normal to the side would be radially outward, and that would be in the horizontal direction. So that's where that cosine 90 comes from. The 90 degrees between horizontal of the area vector and the vertical of the electric field vector. So the side pieces cancel off with zeros, and you're just left with the top and bottom, and of course the top and the bottom, oh, I haven't plugged that in. Yes, the top and the bottom have the same area, and I'm just going to call that A. Then I can figure out that the Q enclosed, which I just shaded in, if you go back up and look at the picture, is that much of the sheet. So the whole point of one of the points of drawing the Gaussian surface is how much charge did you enclose, and it's sigma times that same area. So sigma was charge per unit area, surface charge density. So if I multiply that times area, I get Q enclosed, and so that's what I have, sigma times area replacing that Q enclosed. So this Q enclosed becomes sigma times the area. That's it. We're ready to evaluate. I can cancel off an A on both sides, and I'm left with the fact that the electric field equals sigma over 2 times E0 away from the sheet. That is the electric field due to a uniform sheet of charge. In the original problem, it actually did say something very specific, so I'll write one more form. But a couple things to notice. It's a constant. It does not depend on that h. Even though there was an h in the initial problem, you notice there's no h in our final answer. There's only a sigma, back down to our formula over here, there's only a sigma, which is a constant for this particular problem, and an E0 and a 2. All of those things are constant. So our final answer for electric field is constant. The original question did specify a distance h above the sheet, so we can answer with a full vector equation that the electric field at distance h above the sheet is sigma, which is given in the problem, over 2E0 in the j hat direction. So j hat is our typical straight up, as we already drew.